Hi everyone, this is Jumana Khanfar from Taqarub International Schools. In this lesson, we are going to study rational functions. Rational functions are in the form of p over q, while p and q are both polynomial functions. At first, we will remember how to factor polynomial expressions with some special cases. Then we will discuss the graph of some rational functions and some properties of the graph, like the discontinuity and the asymptote. For the sad subject test, you need to know the vertical asymptote and the horizontal asymptote, but you don't need to study the oblique asymptote. Let's start. These are some rules to factor polynomial expressions. Factoring an expression means that you write it in the simplest form. For example, if you have x squared minus y squared, this is x minus y times x plus y. Like if you want to factor 25 minus a squared, 25 is 5 squared, so this is like x squared, and a squared is like y squared. So this is equal to 5 minus a times 5 plus a. Now, for the sum of two cubes, x cubed plus y cubed, this is x plus y into x squared minus xy plus y squared. For example, if you have x cubed plus 27, this is x cubed and this is 3 cubed. This is gonna be x plus 3 times, let's apply the rule, x squared minus xy, which is x times 3 or 3x, plus y squared or 3a squared, and that's 9. What if we have x cubed minus 27? The rule is almost the same, but we change the two signs here and there. It's gonna be x minus 3 into x squared plus 3x plus 9. Now another important rule to remember is, for example, x squared minus 5x plus 6. We look for two numbers with a product of 6 and a sum of negative 5, and these two numbers are negative 2 and negative 3. In order to understand rational functions, we need to discuss some graphs of different rational functions. The graph of x plus 1 is the graph of a linear function that intersects the y-axis at y equals 1. Okay, now let's graph this, x squared minus 1 over x minus 1. For a more accurate graph, let's see it on a graphing calculator. The graph of this function is similar to the graph of x plus 1, except that we have a hole here at the point 1 and 2, because this function is not defined when x is equal to 1. Because x equals 1 is the 0 of the denominator. Now let's apply the rules of factoring on this and see how can we get this linear function. X squared minus 1 is equal to x minus 1 times x plus 1 over x minus 1. These two cancel out and we got here x plus 1. It's the same as this function, but there will be a hole at x equals 1 because it is a 0 of the denominator of the original function. You might not see this for most of the graphing calculators because of the resolution of the graphing calculator. So you cannot depend on the calculator to tell whether there is a hole or not. You need to understand the properties of the function. Now let's discuss the graph of f of x equals 1 over x. 1 over x is defined for all real numbers except for x equals 0. As we see here, it It's not defined when x equals 0 because the function approaches the y-axis without intersecting it from both sides, and it also approaches the x-axis without intersecting it. This is what we call the asymptote. The equation of the y-axis is x equals 0, and the equation of the x-axis is the line y equals 0. So this graph has two asymptotes, a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Actually, that's why rational functions are considered special, because they have properties the regular polynomial functions don't have. So an asymptote is where f of x approaches without intersecting. And as we said before, for the sad subject test, you need to study the horizontal asymptote and the vertical asymptote. For this function, f of x equals 1 over x minus 2. It's defined for all real numbers except for x equals 2 because it has a 0 of the denominator. This is the graph of 1 over x minus 2. It has two asymptotes, one horizontal asymptote and one vertical asymptote. The vertical asymptote is at x equals 2 because the function is undefined at x equals 2. If we zoom in here, we see that the graph of the function approaches the line x equals 2 without intersecting it. What about the graph of f of x equals x minus 2 over x squared minus 4? It has a graph with a vertical asymptote at x equals negative 2 and with a hole at x equals 2. Now, how can we tell where the vertical asymptote is without graphing? To find where the vertical asymptote is, you need firstly to factor the expressions and represent the function in its simplest form. The denominator here is factored as x minus 2 times x plus 2. These two terms cancel out, and it is similar to the graph of 1 over x plus 2, except that there is a hole at x equals 2, and we saw that hole here at x equals 2. So we can tell where the asymptote is without graphing by simplifying the function and finding the zeros of the denominator. In this case, we have 1, 0, x equals negative 2. And before we simplify, we have a 0 here at x equals 2. That's why we have a hole at this point. So, to tell where the vertical asymptote is without graphing, you need firstly to factor. This is number 1. Then simplify the function. After that, you find the zeros of denominator. This is step number 3. And the asymptote is where the zeros are. The asymptote is represented by the equation x equals c. C is a constant and it is the zero of the denominator. We sometimes have more than one asymptote. For example, if I want to graph the function f of x equals 1 over x squared minus 4, I will have two asymptotes at x equals 2 and x equals negative 2 because they are both zeros of the denominator. We see here that we have two vertical asymptotes at x equals negative 2 and at x equals 2. Now, if we graph this function, we see that it has a horizontal asymptote at x equals 1, and it has two vertical asymptotes at x equals square root of 5 and negative square root of 5. We learned how to find the vertical asymptote by finding the zeros of the denominator. Now, how can we find the horizontal asymptote without a graphing calculator? The degree of both the numerator and the denominator is 2. We take the variable with the highest power in the numerator and in the denominator. This is gonna be x to the power of 2 over x to the power of 2 again, up and down. If we divide these, we get 1. So the horizontal asymptote is at the line y equals 1. What if the coefficients here are different? Let's say 3 and 2. The horizontal asymptote will be at y equals 3 over 2 when you divide 3x squared over 2x squared. And this is 3 over 2. We see here that the horizontal asymptote is at y equals 3 over 2 or 1.5. So if the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is found by dividing the two coefficients of the leading terms. Now what is the horizontal asymptote for f of x equals 3x cubed plus 2x squared minus 1 over x squared minus 5. As you see here, the degree of the numerator is 3, while the degree of the denominator is 2. Again, we take the leading terms. This is 3x cubed, and this is x squared. If we divide these, we get 3x. As you see here, there are no horizontal asymptotes for this graph, because the degree of the numerator is greater than the degree of the denominator. Mathematically, if you divide these two expressions, you get a linear expression. And if we graph a linear function, the linear function does not have any asymptotes. So we conclude that if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. But of course, there are two vertical asymptotes at the zeros of the denominator, which are square root of 5 and negative square root of 5. The zeros of the denominator are positive and negative square root of 5. Now, what if the degree of the numerator is less than the degree of the denominator? In this case, the horizontal asymptote will be y equals 0. Because if you divide the two leading terms, this is 3 over x, and if you remember the graph of 1 over x, it has a horizontal asymptote at y equals 0 or the x-axis, and it's the same here. As you see, it has a horizontal asymptote at y equals 0 or at the x-axis, and it has a vertical asymptote at the 0 of the denominator. The 0 of the denominator is, when you solve this equation, x cubed minus 5 equals 0, x cubed equals 5, x equals cube root of 5. This is the 0 of the denominator, which is almost 1.7. As you see here, it approaches 1.7. But it will never be equal to 1.7. This is enough for this lesson. In the next lesson, we will study the limits or the end behavior of the rational functions.